Hello friends, in the previous videos, we have discussed mechanics in relation to rigid bodies like blocks and wedges. Now, you might wonder how these principles are applicable on human body? As an example, 20 Newton force is required to push a box of 40 kg from point A to point B. However, when the same weight human is pushed with the same amount of force, he might not move at all. So, why does this happen? Stay tuned to understand basic kinetic principles. At the end of this video are some easy techniques to help you remember these principles for your exam, a cheat sheet. Before we start, make sure to subscribe and press the bell icon so you don't miss any new content. With that, let's begin learning. Remember that force is a push or a pull. As in the picture, see, one boy is pulling the block, another is pushing. All forces have a magnitude, that's the amount, and a direction. In this case, both these guys are pulling in one direction. Force can be internal, or they can be external. Internal forces in this case are applied by the boy who's pulling the block, whereas external force is friction between block and ground. We're going to learn the following principles in today's video: tension, compression, shear, bending, and torsion. Let's look at tension first. In simple words, tension is generated in an object when it is pulled apart from two sides. Like this bar pulled from either side, or the tension on rope in tug of war. The human body scenario is different though. Tension is placed on humerus or arm bone when you're hanging on a bar. Here the arm bone is pulled from its ends as it attaches to scapula on one end and forearm bones on the other. The tension stress develops longitudinally in the bone. On the other hand, if there is high tension load, ligaments or tendons may sprain or rupture, muscles might be torn, or bones can be fractured. Compression. Compression forces are the ones wherein force is applied at both ends of an object towards the center, like compressing the rod or the springs of your mattress when you sleep over your bed. The human example of compression force can be seen in standing position. Femur and tibia are under compressive forces because the weight of your body is pushing them down from above, whereas there is ground force is pushing up from below. However, intense compressive loads cause crush fracture of bones, usually seen in road traffic accidents or industrial accidents. Shear. To understand shear, consider two externally applied forces that are equal in magnitude and applied in opposite directions, but are not in line with one another. These are shear forces. Like this block being given two forces from its ends. Usually, we see scissors work on this principle. The ends of scissor cut the paper as force is applied from two ends which are not in line with one another. In human bodies, high magnitude of shear force causes joint dislocation, or shear fractures of bones. Bending. Bending is when compressive and tensile properties of an object are put to test. You can see the rod bent or trees bent because of rough wind, and if their trunk is not flexible enough to bend, they may break apart. In humans, bending can be seen when a person is in single support and walking, essentially a one-legged chair. The femur experiences bending loading. The medial aspect of the femur is in compression, while the lateral aspect is in tension, thus bending moment is created at hip joint. Torsion. If two equal, parallel, and opposite forces are applied perpendicular to the long axis of a structure, they constitute torsional loading. Like a sponge is turned in two different directions as shown in the picture, or like you wring clothes after washing them. For another example, take a pencil and twist it in one direction with your right hand and in the opposite direction with your left hand. What happens is you're inducing torsional loading on the pencil. If we only consider the force on the left side, the pencil is not in equilibrium, but has a rotational force or torque that would cause it to spin, but there is internal torque that creates shear force between left and right side of the pencil. This internal torque counteracts the external force or torque on left side, thus creating shear force at the center of the pencil. The internal torque on either side of the center is limited to the diameter of the object. For example, for pencil this moment arm is small so counter internal force must be large to resist, but if the stresses become too large the pencil breaks. The smaller the diameter, the larger internal torques it needs to generate to withstand small torsional loads. In the case of bones, they have large circular cross-section because larger diameter means they must produce smaller internal torques to withstand large magnitude of torsional load. That is all for today. We'll understand strain and stress-strain relationship in the next video. If you have any questions, drop them in the comment section. I would love to hear from you. Like, comment and share if you like the content.